Hi everyone, welcome back. So now we'll talk about closed pipes versus open pipes, right? So in the previous video, we saw how vibrating strings work. So that is a prerequisite to understand this video. In vibrating strings, the fundamental frequency is 1 by 2L square root of T by M. And for the higher modes of vibrations, we have the second harmonic, the third harmonic, the fourth harmonic, and so on. So basically all the harmonics are present in the case of a vibrating string, right? So now coming to our closed pipe. Okay, so as you can see, I have drawn three pipes here, right? All three of them are closed pipes on the left, whereas the three pipes on the right, they are open pipes. So what do we mean by a closed pipe? Obviously we cannot have a pipe closed at both the ends, otherwise we cannot have a sound wave entering the pipe, right? So closed pipe means it is closed at one end, and open pipe means it is open at both the ends. So on the left as well as the right, I have three cases, right? So we will talk about the fundamental mode. The first one will be the fundamental mode of vibration, and then the first overtone and the second overtone, right? So we'll talk about three cases and then we will generalize just like what we did in the vibrating strings. Okay, so let's start with our closed pipe, fundamental mode for the closed pipe. So one thing is clear that if one end is closed here, right, then we are going to have a node at the closed end. There has to be a node at the closed end. So how will we get our stationary wave in both the cases, right? We can keep a tuning fork in front of one of the opening, right? So let's say the right opening. We can keep a tuning fork, so the sound waves will enter the pipe from the tuning fork. The incident wave will get reflected here at the closed end, and because of that there will be a reflected wave. So the incident and reflected wave will interfere and it will give us a stationary wave in case of a closed pipe. Well, then you may ask that what about the open pipe, because if the wave enters the open pipe from the right hand side, then what's going to happen is that the wave will just come out, right, from the open end. So if the wave simply comes out of the open end, then how will we get a reflected wave, and how can we have a, how can we have interference between the incident and the reflected waves, right? So the answer to that is basically what is happening here in the case of an open pipe is that the wave is going from the air in the pipe, right? There is air in the pipe and there is air outside the pipe everywhere else. So what's happening to the wave is it is going from a bounded medium to an unbounded medium, right? Bounded to unbounded medium. And because of that, what's going to happen is there will be some reflection here at the open end, right? The wave will come out as well as there will be some reflection here, and that incident and reflected wave can interfere, right? The incident coming from the right hand side towards the left and the reflected wave, right? They will interfere and they will give us a stationary wave, right? So we will get stationary wave in both the cases. Okay, so coming back to our closed pipe, we have a node, right? The closed pipe, the closed end of the pipe, there has to be a node because the last air molecule there will not be able to vibrate. Now again, if I want to draw the waves inside both these pipes, then obviously I'm talking about a sound wave, right? Whereas the wave in the case of a string was it was the wave of the string, right? So it was a mechanical wave, whereas here I'm talking about a wave of sound. In the case of a string, the particles of the string were vibrating up and down, so we were having SHM. Whereas in the case of this pipe, both the pipes, right, what is happening is we have air molecules vibrating. So we have a sound wave which is a longitudinal wave, whereas in the case of a string it was a transverse wave, right? Now we have a longitudinal wave, right? So we have compressions and rarefactions. So again, if we sit and draw compressions and rarefactions, it's going to be very tedious. So what we will do is instead we will represent Okay, so this word is important. We will represent that longitudinal wave by a transverse stationary wave instead of a longitudinal stationary wave. Just for representation, just for drawing, right, drawing inside, we will draw a transverse stationary wave, right, which actually can even be considered as a graph. Actually speaking, if you want to be more clear, what we are going to draw inside is, we will draw a graph of amplitude of vibration versus distance along the length of the pipe. Okay, a graph of amplitude on the y-axis and distance on the x-axis, amplitude of vibration of the particle. Okay, so let's draw the graph. Okay, or let's draw the wave. So if I have a node at one end and the other end, because it's open, right, so the air molecule here is free to vibrate, so I can consider there must be a antinode here, right, in all the three cases, right. So how will we get our wave here? So the fundamental mode must be, there is one node, there is one antinode and nothing in between. Okay, so we can get a wave like this. So as I said, all I am drawing is just a representation, and that's why I'm drawing it in dotted lines, right. It's a representation of the wave inside. So that's my representation of the longitudinal stationary wave. I'm drawing a transverse stationary wave. What I've drawn, a crest and a trough, a part of the crest and the trough, right. So that's a transverse stationary wave, but mind you, it's not a transverse stationary wave inside the pipe. Okay, and what would be the next mode of vibration? So instead of having one node and one antinode, I can have two nodes and two antinodes. So how would that be possible is, you start from your node again, so something like this. So as you can see, we have a node, adjacent to the node we have an antinode, and then again here we have a node, and then again a antinode. So two nodes, two antinodes, that's the next higher mode of vibration, right. So this is the fundamental, this would correspond to the fundamental frequency, this will correspond to the first overtone, and this third diagram would correspond to the second overtone. So one node, one antinode, two nodes, two antinodes. Now we will have three nodes and three antinodes. So how to draw that? Right, something like this, and then so as you can see, there's a node here, antinode, again a node, again an antinode, again a node, and the last one is obviously a antinode. Okay, so that's your diagram for the three closed pipes. Now what about the open pipe? So again, since both the ends are open, right, and the open end means the last air molecule on both the sides, it is free to vibrate, or in other words, it can vibrate with maximum amplitude. So I will have an antinode at both the ends, not just one end. That's the difference between your closed and the open pipe, right. We can have an antinode at both the ends. Again, if you want to talk about the fundamental mode, then in the fundamental mode of vibration, the fundamental frequency, right, corresponding to the fundamental frequency, two antinodes. So only one, there has to be one node in between, right. There can't be two antinodes and nothing in between. There has to be one node. So how can I draw my wave? So again, it's a longitudinal stationary wave inside, but we are drawing it, right, or we are representing it by drawing a transverse stationary wave, or in other words, we are drawing a graph. Again, it's a graph of, on the x-axis there is distance, on the y-axis there is amplitude. Just like, for example, if you consider this fundamental of the closed pipe, if I consider the x-axis as distance or length along the pipe, and if I consider the y-axis as amplitude, then here the particle here, if I consider this node here as the origin, it can't vibrate, so the y value is 0, whereas the particle here can vibrate along the y-axis. I mean, along the y-axis I'm drawing amplitude, so it can have a positive amplitude as well as a negative amplitude, or in other words, it is actually vibrating left and right, but the left and right vibration I'm drawing it as up and down. That's why I said it's a representation, right? Okay, so coming back to our open pipe, so all of them, all the 6 diagrams here are going to be the graphs. Okay, so we have an antinode to begin with, a node in the center, and then again an antinode. So we will get a graph something like this. Sorry. Right. And then okay, so it should be more smooth. Okay, so as I said, there is one node in between. Okay, so that's 20 nodes, one node. Next higher mode of vibration, the first overtone. This will correspond to the diagram for the first overtone. So I start with an antinode, so 2 antinodes, and there will be one more antinode in between, so there will be 3 antinodes and 2 nodes, right? So how do we draw that? So something like this. So we have an antinode to start with, then the adjacent node, then one more antinode, one more node, and then the last one is antinode. So we have 2 nodes, 3 antinodes, and similarly the next mode of vibration would be like this. So now we have node, antinode, then a node, antinode, node, antinode, node. So I have one node, 2 antinodes, 2 nodes, 3 antinodes, 3 nodes, 4 antinodes, right? That's how the diagram is. So now moving ahead, we want to get the formula for the fundamental case, and want to see what about the overtones, right? So the length of the pipe, right, if I call it as because it's a closed pipe, let me call it as LC. So what is the length of the pipe here in this diagram? How much is it? Node to antinode, the distance can be called as lambda by 4. What about the second diagram? How much is LC? It's the same length, right? It's the same value of LC, but now it is node to node, which is lambda by 2, plus node to antinode, which is lambda by 4. So 1 by 2 plus 1 by 4 will give me 3 by 4. So I can say 3 lambda by 4, but to be very clear that this wavelength and this wavelength are different, I can just put a lambda dash, right? Whereas here the LC value would be node to node and then another node, so that forms one wave. You can see here one wave, so one wave is lambda by 2 plus node to antinode is another lambda by 4. So 1 plus 1 by 4 will give me 5 lambda by 4, but again the wavelength here, here and here, they are different, so let's call it as lambda double dash. Okay, and if I want to do the same kind of comparison here in the case of an open pipe, so because it's an open pipe, let's call it as LO, right? So how much is it equal to in the three diagrams? Antinode to antinode, so that's obviously lambda by 2. Antinode to antinode is lambda by 2, and another antinode to antinode is another lambda by 2, so I get lambda. But again, I want to distinguish between the two wavelengths, so I'll call it as lambda dash. And again you can see antinode to antinode to antinode, so that will form one wave. You see I'm starting from a crest here and then reaching another crest, so that's one wave. And then again antinode to antinode is another lambda by 2, so 1 plus 1 by 2 will give me 3 lambda, but it's different than these two, so I will say 3 lambda double dash divided by 2. Okay, so now that we have got the lengths, right, for the three cases, let's try to derive the formula for the fundamental, and then also talk about the first and the second overtone. So what can I say in case of the fundamental mode here, the fundamental frequency? First of all, I can say lambda is 4 times LC. This is from the diagram. And then if I simply use the fact that V is n times lambda, I'm going to get, and because I have the fundamental case, let me call it as NC, I'm going to get NC is equal to how much? V by lambda, but the lambda value I know from here, it's 4LC, right? And this gives me the formula for the fundamental frequency of vibration of my closed pipe, V by 4LC. Okay, now what about the first overtone? So I'll use a different color. So I can now say lambda dash is going to be 4LC divided by 3, okay, from here, and therefore the velocity is going to remain the same, but the wavelength has changed, the frequency has changed. So let's call it as n dash lambda dash. So I'm going to get n dash, right? What is it going to be? It's going to be V by lambda dash, but lambda dash I know is 4LC upon 3 goes in the numerator, or in other words, I am getting what? 3 times the fundamental frequency NC, because V by 4LC is nothing but NC. Whereas in the third case, I can say lambda double dash now. Lambda double dash is going to be 4LC divided by 5. So now my V value is n double dash lambda double dash, or in other words, I'm getting my n double dash as V by lambda double dash, but lambda double dash is 4LC divided by 5, which goes in the numerator, so I'm getting 5 times NC. So after the fundamental, I am getting the third harmonic, the fifth harmonic, if I go ahead, the 7th harmonic, and so on. So if I want to generalize, how can I generalize it? I can say NP, where P is the overtone, right? it's going to be, because I want the odd numbers 1, 3, 5, 7, 9, I will say 2 times P plus 1 in C. So we can check this formula by substituting the values of P and verify here. So this is the first overtone. So if I want n1, or which I have called as n dash here, let's call it as n1. What will it be? 2 ones are 2 plus 1, 3 NC. If I want n2, 2 to the 4 plus 1, 5 NC. If I want n3, 3 to the 6 plus 1, 7 NC, and so on, right? So this becomes the formula which will give us the overtones. This is my formula which will give me the fundamental frequency. Similar kind of discussion here for our open pipe, right? What is the value of lambda? It's going to be 2 times LO from here, 2 in the numerator. So if lambda is 2 LO, I know V is equal to n lambda, but because it's the open pipe, let me call it as NO lambda O. Or in other words, what is the fundamental frequency NO? It is V by lambda, but lambda is nothing but 2 LO, right? So this is my formula for fundamental frequency for a open pipe. Okay, next the first overtone here. So lambda dash is equal to, it is equal to LO, but what we could do here is, because we have 2 LO here, so how can I express it as 2 LO? I can just say 2 LO by 2 is nothing but LO, right? Lambda dash. So now again the same thing as what I did here. V is equal to n dash lambda dash, velocity doesn't change, and therefore n dash is going to turn out to be V by lambda dash, but lambda dash is 2 LO upon 2 goes in the numerator, so I am getting 2 times NO. V by 2 LO is NO, so I am getting 2 NO, that is the second harmonic. And if I move on to the next case, I have lambda double dash now. How much is that? It is 2 LO upon 3. So if I use this, I'll get same V is n double dash lambda double dash, or in other words, n double dash is going to be V upon lambda double dash, but lambda double dash is 2 LO upon 3. So I am getting now 3 times NO. So I got the fundamental, I got the second harmonic, I got the third harmonic, I'll get the fourth harmonic, and so on. So here in the case of an open pipe, if I want to generalize and get a formula for the pth overtone, what is it going to be? It is not just an odd number, odd harmonics, the even harmonics are missing here, but here in the case of an open pipe we have the odd as well as the even harmonics. So it's going to be P plus 1 and O, and again you can verify whether this formula is correct by putting the values of P. If I put P is equal to 1, I'll get the first overtone, I'll get 1 plus 1 2. If I put P equal to 2, I'll get the second overtone, 2 plus 1 3, and so on, right? So NC is V by 4 LC, NO is V by 2 LO, NP is 2P plus 1 NC, and here NP for a open pipe, right, it's P plus 1 NO. These are the formulae, the main formulae that we need to know in case of a closed and a open pipe.